1970, both from Kyoto University. He served as an assistant professor at Kyushu University until 1976 and went on to be an associate professor at Kyoto University until 1981 before becoming a full professor until 2004. And after returning from Kyoto University, he held positions such as specially appointed professor at Hokkaido University, visiting professor of Kyoto University and deputy director at the International Institute for Advanced Studies, which I think also is a part of Kyoto University. His major awards include the Asahi Prize in 2005 and Jürgen Mosher Lecturer Prize in 2023. So the citation, I'm following the citation from the Boltzmann Medal Committee. So Professor Kuramoto received the Boltzmann Medal 2025 for groundbreaking work on non-equilibrium systems, especially nonlinear oscillations, synchronization, and weak turbulence. So Professor Kuramoto's work on spatially extended chaos, resulting in the celebrated Kuramoto-Shimanoski equation, laid the ground for further development of nonlinear science applied across a wide range of disciplines. The Kuramoto model established the scientific field of coupled oscillators, a vibrant area of nonlinear science and complex systems with profound connections to statistical physics. So when I reached out to Professor Kuramoto, so he said that he cannot give an online talk. So he sent us a pre-recorded video. So that is what we are going to put it here. And after this is gets over, Professor Mehran Kardar will join online, and that will be an online live talk. Okay. So I think without further delay, we can just put on this pre-recorded video. And of course, I won't be able to give any answer to this.
Well, to be invited to this wonderful meeting. For some reasons, online, but please allow me to send you a video message instead. In this message, I will tell you quickly some historical background of how my oscillator model, called the Kuramoto model, came out, and how this model influenced the subsequent advances of the field of coupled oscillators and synchronization. Well, I hesitate to mention my own name, Kuramoto, so frequently below, but please understand that this is something unavoidable. Well, over nearly half a century in the past, I have mainly worked on the dynamics of light systems of self-sustained oscillators. Well, in fact, self-sustained oscillations or persistent rhythmic phenomena are found everywhere around us. Just think of our heartbeat, our walking steps, and internal clocks. We are always living with rhythms. Also think of flapping birds, flashing fireflies, and chirping crickets. Even lifeless things exhibit rhythms. Waves repeatedly hit the beach. A clock ticks periodically, and violin strings vibrate. Well, it's natural happen that rhythms meet each other. When something mysterious occurs, they start to synchronize their steps as if they recognize with each other. So, if we say that rhythmic phenomena are ubiquitous, then synchronization is also ubiquitous. As is well known in history, the first person who observed synchronization from scientist perspective was Christian Huygens the 17th century Dutch scientist, while he was watching the synchronous motion of two pendulum clocks. Collective flashing of fireflies also amazed and intrigued people for a long time. So people's interest in synchronization has a long history. Still, there had been little progress in the mathematical understanding of synchronization until the middle of the last century. And it seems that this is partly due to the fact that mathematical description of just one sustained oscillation requires a mathematical concept of loop cycle, which is a hard mathematical object to handle analytically. Even worse, its orbital shape and the motion around it may largely differ from system to system. So it seems that mathematical description just mutual synchronization of just two oscillators would be even harder, not to mention the synchronization of large populations of coupled oscillators. I think Art Winfrey was the first to open up the way leading to the right solution of this hard problem. He did this in his seminal paper published in 1967 entitled Biological Rhythms and the Behavior of Population of Coupled Oscillators. In those days, I was a researcher of the traditional statistical physics. And like the researchers in the same field at that time, I wasn't so familiar with mathematical biology, so it was 7 years after the publication of Winfrey's paper that I finally came across it. Well, Winfrey's paper gave me a strong impression in the following two ways. First is that he broadly described the length cycle oscillator only in terms of one variable, that is phase. And so the mutual coupling between two oscillators depends on two phases. By doing so, he succeeded in creating a simple mathematical model for a large assembly of coupled oscillators. By the way, describing coupled oscillators only in terms of phases is justified generally whenever the mutual coupling is sufficiently weak, as was confirmed later by many theorists. Another point which Winfrey's paper surprised me was that he claimed the existence of a critical condition for the onset of collective oscillation. This is a kind of order disorder transition similar to thermodynamic phase transition. But unlike macroscopic bodies composed of inactive elements such as atoms and spins, here the system is composed of dynamically active units, oscillators. So since I had some background of statistical mechanics of phase transition, such a new type of phase transition was a fresh surprise to me. By the way, phase transition results from the competition between the randomness and the ordering force of coupling. And in Winfrey's paper, randomness comes from the random distribution of intrinsic frequencies of the oscillators. So this means that his model represents a deterministic dynamical system of infinitely high dimension. And this point also made me feel quite exciting. Well, unfortunately, however, his verbal argument on the existence of phase transition was not so convincing. So I wished to somehow modify his model and transform it to a mathematically tractable model, maintaining the original form as much as possible. And actually, this was not so difficult for me. What was needed was only to replace his coupling function with the simplest trigonometric function, that is sine function, depending only on phase difference between the interacting pair. The resulting solvable model is nowadays called the Kuramoto model. Exactly 50 years have passed since the proposal of this model, and fortunately this model captured considerable interest of researchers from a wide range of fields, including mathematics, nonlinear dynamics, statistical physics, biology, brain science, and even modern technology. Well, it's true that when I came up with this model, I was a little happy, but not more than that. So what I did was just to present a short talk at the international symposium held in Kyoto and submit the brief report, its brief report to the proceedings. I think if I had written a little longer and careful paper, then my model would have caught the attention of a wider audience. So it's not surprising that my model remained unnoticed for several years after that. Perhaps it was Winfrey again who first found out my short article and highly evaluated it, referring my work in his monograph published in 1980 entitled The Geometry of Biological Time. Encouraged by this, 4 years later, I present a more detailed account of my own model in my monograph, Chemical Oscillations, Waves and Turbulence, published in 1984. Well, let me have a few more words about what I did and also what I didn't but left unsolved. As I said, the concept of collective oscillation is similar to a thermodynamic phase transition, especially the second order phase transition of ferromagnetic spin systems. And following Winfrey, my model employed global coupling, and this means that the elementary idea of the mean field theory of magnetic phase transition seemed applicable. Well, in fact, this was achieved by introducing a suitable order parameter, which measures the strength of collective oscillation. And, in fact, although there were some non-trivial problems peculiar to synchronization phase transition, by posing some hypothesis, a self-consistency equation for the order parameter could be derived successfully. And its solution clearly shows the existence of critical coupling strengths across which non-trivial branch of collective oscillation emerged from a trivial solution of stationary state, constant solution. But how about the stability of these solutions representing macroscopic states? It seems that there is no way to determine the stability. Although I will skip all details, putting it shortly, if we try to examine the stability, then we are faced with a problem of spectral anomaly. That is, our spectrum is distributed continuously on the imaginary axis, and this makes the standard stability theory inapplicable. This unusual type of stability problem aroused considerable mathematical curiosity, and it took more than 20 years until this issue finally had a satisfying solution. Well, as putting the stability issue aside, near the turn of this century, a new model for complex networks appeared in succession. One is the small world network of Watt and Strogatz, and the other is the scale-free network of Barabasi. And owing to the appearance of the network models, the science of coupled oscillators and synchronization also expanded its research domain greatly. But before the sudden appearance of these network models over nearly a quarter century, the study of the dynamics of coupled oscillators in large systems had concentrated exclusively on the systems of regular coupling topology, classified only in terms of the coupling range, such as global coupling, local coupling, and their intermediate, that is non-local coupling. But with the sudden appearance of network models, a new challenge emerged. And focus of interest there was what the relation is between the network topology and the dynamics on it. Well, there appeared a tremendous number of research works on this issue. But I will no longer go into this issue, but I think I should mention one innovative theoretical achievement of Edward Ott and Thomas Antonsen, who succeeded in drastically reducing the dynamics of Kuramoto type globally coupled system to extremely low dimensional dynamics, thus enabling describe the order dynamics equation in a closed form. Well, the impact of Ott Antonsen's works was remarkable, and the impact was remarkable, and as a result, a tremendous number of research works appeared in this area. Well, in parallel with these theoretical innovations, various modifications of the original Kuramoto type oscillator model were also proposed. Other than considering different coupling range and different coupling topology, various modifications were proposed. For instance, the explicit time delay in the coupling, and an inertial term was added, and pair coupling was replaced with higher order coupling, and so on and so forth. And such modifications were partly required from the practical purposes. For instance, if one wishes to apply the Kuramoto type oscillator model to power grid synchronization, then inertial term needs to be introduced. Well, in conclusion, I would like to say that the science of coupled oscillators and synchronization has developed to form a field spanning extremely broad scientific disciplines, not limited to a small part of nonlinear science and statistical physics. Personally, I am particularly concerned with the synchronization in living systems. One reason for thinking so is that when we consider the evolution of life, living systems should have exploited any dynamic mechanism available for their survival. And there is no doubt that synchronization is one of such dynamical mechanisms of extreme importance. So, as we understand better how life exploits, cleverly uses this synchronizing mechanism, then modern technology will also learn a lot from it. Wishing for further development of science of coupled oscillators synchronization. Thank you very much.
So we'll try to see Gayatri, is it there? Can you please check your chat box? To the online participants, so I actually regret to inform you that I have not been able to connect with Professor Kardar. So although this time and etc. was decided, but somehow I think maybe there might be some network issues or something like that. So we have been waiting for some time, and for the interest of time, I think we have to close the Zoom meeting. So I will try to reorganize this maybe in near future sometime. Thanks for joining, at least for the first talk, and okay, so thank you very much.